Okay, so let's move on. Um,
So the main set A, that has to be closed, right?
yeah, otherwise, where would you get a boundary? Open sets don't have any boundary.
Okay. So uh, the set A, if I don't consider the boundary, that's A angstrom sign.
If you don't consider the boundary, are you talking about the interior?
Yes.
Yeah, that's your A angstrom or
Oh,
A0, whatever you want to call them.
okay, got it.
Okay. Okay, now let's define something called compactness. Uh, let X and tau be some be topological space. Then a family of sets, or so to say, a family of subsets of X. Then a family subsets of X, which are given by some with some index family, or so to say index notation, which is a Y, is called covering covering of X if this union is resulting in the space that you started with. So you have a topological space, you have some subsets, you take their arbitrary union and you get back this X, then it's called a covering. In some sense, these sets A, they are making X up, or they're building X up. So that's why people maybe call it a cover, or so to say it covers the whole X or something like that. But this is the definition of a covering. And if your A's are open, if these sets AIs are open, then it's called an open covering. And with the definition of covering, we can move to the definition of compactness. So now consider the set X and all possible coverings of capital X. The set X is said to be compact. X is said to be compact if for every open covering, open covering, what do we mean? We mean all the sets we defined over here, the sets called A's, they're open, and all those open coverings, uh, let's denote them with some u of I. Since we're calling them open, we are changing the notation, because at first we didn't, when we defined the covering thing, we just said, oh, these A's are subsets of X, right? We didn't say anything about open or closed. But then we said, oh, this if these A's are open, then we call it an open covering. And then we are telling, oh, this, we can call this topological space X to be compact if for every open covering that is given by, this Q, again an index family, there exists a finite subset J of I such that U of J, where J belongs to J, is also a covering of X. So let me try to break this down a little bit. Um, First, look at this line. First of all, we understand what is covering, right? And we understand what is open covering. So what it says in the definition is that your X is a topological space. And we are considering all the possible coverings of X, right? Then the set X is said to be compact if for every open covering. That means each and every open covering. Like all the, I have written it as UI just to, you know, embed the fact that these U's are your covering, but they're open coverings. So here I used A. I could have used U as well. Usually when you write open sets, people use this U. You can even write A of I if you understand that those are open coverings or open sets and stuff. So for each and every open covering, there exists a finite subset J of I. What is J of I? Well, if you recall, what was I? I was a family of index, right? I could be 1, 2, 3, 4, yada yada yada. And J is a subset of I. That means if I contained all the elements from 1 to 100, let's say, J could contain, some 1, 2, 3, 4, 5, 6, up to 6, let's say. Okay, is that understood? What do I mean by J is a subset of I?
They don't have to be in sequence, right? They could be just random ones,
Yeah,
29,
exactly.
34.
Yeah, exactly. So that's what I mean by a subset. Like if you had 100 of numbers in I, you could have 20 numbers in J, something like that. These are index families or index sets, so to say, such that all the open sets that you can construct from these J indices is also a covering of X. So think of it like this, okay? You are a person. I mean, that's how I thought of it. I don't know. It seems very stupid because I'm more of a physics person. I'm not a math person. So instead of thinking it mathematically, all those theorem, axiom, lemma stuff, I thought it like this. You are a person. Let's say you can eat 2 burgers at a time, or you can easily eat 4 burgers at a time, but you can easily fill your belly with 2 burgers. So I thought of these burgers, as your open sets that can cover up my bellies or our bellies, whatever you want to call them. But instead of taking 4, I can take 2, and I can still cover my belly. I can still, have a good meal. That's how I thought of this compactness in the first place. Does that make any sense? I mean, that's some stupid physics analog, not physics even, some stupid analog of this definition. That's what this definition tells you. That all the things that you use to cover the space first, it might happen that you don't need all of them. You might even take a subset or a sub collection, and yet you can cover the space totally. So when you can do that, then we call it a compact space. Oh
আচ্ছা,
my god,
তো
what was that?
সরি,
Yeah, no, it's fine.
ইয়ে যে মানে কম্প্যাক্ট না, এটা দেখানোর জন্য কি তাহলে মানে জাস্ট যে কোনো একটা মানে এরকম এক্সাম্পল দেখাইলেই
Counter
হবে না?
example, yeah, one counter example that you
যে
take this
যেটার
definition. Yeah,
মানে সাব কালেকশনের ফাইনাইট ইয়ে দিয়ে করা
yeah,
যায়
it
না?
doesn't cover it. Yeah, one counter example is good enough.
আচ্ছা,
If you don't,
এখন মানে কম্প্যাক্ট প্রমাণ করার জন্য তো আমার একটা ফাইনাইট সাব কালেকশন বের করেই যথেষ্ট, রাইট? না, আমি যদি একটা ফাইনাইট সাব কালেকশন পেয়ে যাই, বাট কম্প্যাক্ট না, এটা প্রমাণ করব কিভাবে?
কাউন্টার
লাইক
এক্সাম্পল দিতে হবে তোমাকে, যে তুমি বলবা যে আমি যেটাই নিচ্ছি আমার পুরোটা কভার হচ্ছে না, মানে এই যে কন্ডিশনটা, এই কন্ডিশনটা স্যাটিসফাই হচ্ছে না। তোমার যে সাবসেট যেটা, হুম, তুমি যে সাবসেট গুলো নিয়ে চিন্তা করতেছো, ওই সাবসেট গুলোর তুমি ইউনিয়ন নাও এইভাবে আরবিটারি, মানে তোমার এই যে ইন্ডেক্সের উপরে রান করতেছো, তুমি তো ইন্ডেক্স নোটেশন বুঝো আই থিঙ্ক। সো এই যে কন্ডিশনটা, এটাই তো কাভারিং এর কন্ডিশন, রাইট? তাই না?
হ্যাঁ,
তো তোমার এই কাভারিং এর যে কন্ডিশনটা, অবভিয়াসলি ইউ আর ডিলিং উইথ ওপেন কাভারিংস, সো ইউ হ্যাভ টু মেক শিওর অফ দ্যাট। যদি ওইটা পাস করে, দেন সেকেন্ড স্টেপ হচ্ছে যে তুমি যদি প্রুফ করতে চাও যে এটা আসলে কম্প্যাক্ট না, তখন হচ্ছে তুমি যে সাব কালেকশনটা নিয়ে কাজ করতেছো, ওটা তো তুমি দেখাবে and you have to prove যে কোনো সাব কালেকশনের জন্য ওইটা কাজ করবে না। যদি সেটা না করে তখন বলতে পারো যে এটা কম্প্যাক্ট না। বুঝতে পারছো?
আচ্ছা।
সো এখন ওকে, এনিথিং এলস, এনিওয়ান?
Does that mean in some sense that all the possible coverings have some sort of overlap, which is why we can take a subset of them and still create a covering? Like
Sorry, I
we're
didn't get
removing
that. Can you please repeat? I didn't get that, sorry.
Right. So does that mean somehow that every possible open covering has overlap, in the sense that if we take a subset of that open covering, then we can still cover it because we're kind of quote unquote removing the overlap from that set?
No, I don't think so, because um, what you're saying is that, let's say I have, let's say, 4 open sets. Okay, I'm dealing with numbers so that it's easier for everyone to understand. Let's say I have some space. I have 4 open sets or 5 open sets. Let's say 5. Let's take 5 open sets, and what I see is that if I take the union of those 5 open sets, I get my topological space expect, right? So they will act as my covering. Now, if I see that, instead of taking those 5, I can take 3 and I can still cover my space, then we are calling it a compact. So if you are talking about that, are we removing some redundancy? That, some two, there, I think by overlap, you meant some sort of a redundancy, right?
Yeah, I do. Yeah.
I have to think about it. Like, it's not very easy to answer. Like, why would they be redundant? That's the first question that, you logically ask. Okay, why would they be redundant? Uh, mm,
Like there would be some intersection between the two sets that was
Okay.
covered in both of them. Like
Okay.
there would be elements in both sets that had, they were shared elements. So if you remove one of the sets, then like
It really
all the
doesn't make
other
a
sets
difference.
have
It
the
really doesn't.
elements represented.
Okay, so I think we can, make it more explicit through an example, right? For example, take this set, some 1, 2, 1, 2, right? Something like this, and a null set,
Yeah.
right? So if you get rid of this, if you take union of this 1, 2, 1, 2, and null, you still get what? 1 and 2, right? But you can
You
get
don't need
rid of
all of
this.
them.
You don't need all of them, exactly. You just need 1 and 2.
Yeah,
So
that's what I was trying to get at. Yeah.
that's what you're trying to. Okay, so yeah, in this sense, you can think of them as, removing this redundancy of overlapping and stuff. But is it the case in general? That is something I don't know, because
Okay.
I think it's a more mathematical question, so I do not know. So I can ask and I can get back to you people via Slack. So just give me a reminder on inbox that um, that you wanted to address us regarding this topic. Okay. From our explicit case, yeah, that's evident. But is this the case in general? I don't know. Okay, so now let's talk about some physics. I mean, we talked about a lot of maths and stuff. So, oof. So compactness is important. For example, I think what Nakahara did, used some example of, electrons in a solid, that um, he talked about these volumes and cells and all those stuffs to, make the reader understand the importance of compactness. That if you are dealing with a lot of things, if you cannot compactify stuff, then you would get a lot of variables. It would require quantum statistical mechanics and all that stuffs like that, and whatever. And what I wanted to show you is that it's something that you will probably see in your future courseworks. Um, let's say you are dealing with a 10-dimensional theory, or higher dimensional theory. So what you can do is that you can compactify one of the dimensions. It's like saying that, if you're dealing with a three-dimensional system where your x, y, z, they extend from minus infinity to plus infinity, and if you are dealing with some variable, you know, some x, y, z, and your problem requires you to deal with stuffs all over the space, then you have to deal from what, minus infinity to plus infinity, and that's troublesome, right? So what you do is that instead of taking the z-axis, you make it compact. You make it a circle or something. So you have effectively reduced one dimension. This is one of the applications that you will see in your future course. But I think something you will see when you do complex variable. I think most of you have done complex variable. You have heard of this thing, right? Stereographic projection. Stereographic projection. The complex plane is infinite on both of these axes, right? Like this, x, y. This is z. Um, where some z, there's some z which belongs to the complex number. And what do people do in stereographic projection? They compactify this complex space or the complex plane into a sphere, right? So any point in the complex plane can be identified with a point on the sphere, and it is unique, right? And the points of the infinity, they map to these poles. Everyone did a stereographic projection, right? People who did 215 or math 204.
I did not take any course of that.
Oh,
I
okay.
haven't, but I know what the stereographic projection is.
Tibralis showed this. Tibralis sir showed this in
Rafid, you
statistical.
did 215, right?
Yes,
Under me.
yes, yes.
We
I
covered, yeah, we covered
yes,
stereographic projection, if you recall.
yes, I
Yeah.
remember.
So these are the examples of your, compactification. So it's a very interesting thing. Even yesterday, I was, attending a talk by Lara Anderson. She works in these stuffs, and these are pretty interesting stuffs. I don't know what she talked about. I didn't understand on 99% of the stuff that she was talking about, but it was very interesting. So yeah, the definition, the mathematical definition, it might bore you to death. But once you get to do physics with these sort of things, it's pretty fun. It's a fun thing to do. And in bosonic string theory, you compactify one dimension, and when you could do that, you're, okay, who's here? Okay. So as I was saying that when you compactify one dimension, you and you can analyze that, and you can take different limits to see what happens, in large energy regime or in low energy regime, and this sort of interesting stuff. So you'll see that in your future courseworks if you uh, stay in physics. So with that, let's move down to some more definitions, and this time we want to talk about connectedness. Is it 6:30 already? Oh my god. Okay, I think I have to stop at connectedness, but let me just define it before we go. um, a This is the definition of a connectedness. A topological space is by topological space I mean some x, okay, is connected if it cannot be written as x equals to some x1 union x2, where both x1 and x2 are open, and at the same time x1 and x2, they are disjoint. Otherwise, x is called disconnected. So this is the definition of this connectedness. And let me give you two more definitions. Actually three, not two. arc-wise connected, or connectedness when you think about arcs. If your topological space X, let's say you have two elements, some X and Y, which belongs to X. If there exists a continuous map that takes a unit interval and maps it to X, I choose 0 and 1. I think that's the convention. You can choose any unit interval such that f of 0 is X and f of 1 is Y. Then they are called arc-wise connected. So if this is your topological space X, this is more of a visual representation. If you have some unit interval, it takes you from X to Y. Similarly, you can have another point that takes another unit interval and it maps you from, from that unit interval, let's say from 1 to 2, from Y to Z and stuff. So you can define these small arcs to go from one point in your topological space to another. And finally, I define something called a loop. In your topological space X, is this unit interval under some sort of a mapping F, which maps your unit interval to topological space X, but this time your f of 0 is equals to X, small x, this point over here, and at the same time it maps the other end of the interval or the other point on the interval, whatever you want to call it, to the same point, then this is a loop. It's pretty easy to see, right? Your topological space, this is your unit interval, and this is your mapping. This is your point X, and what does F do when it takes in 0? It maps that point to X. Similarly for 1, it maps that point to X, right? So you can have a loop like this, loop like this, like this, like this, and etc. And when you talk about loops, you also talk about, whether your topological space is simply connected or multiply connected. I think if you have done multivariable calculus, there you have some information like this, that if you have some, again, this is from multivariable calculus, you see that if you have a surface like this and you draw a loop over here, if you can shrink it continuously to a point, then we call it a simply connected region. Or if you had a hole, let's say this pink guy is a hole, you cannot shrink it continuously to a point, right? So we call it a multiply connected. I mean, since there is only one hole, people call it not simply connected. If you have two holes, people call it multiply connected, but in general they are multiply connected. So similarly in topological spaces, if you can shrink your loop, let's say this is a loop, if you can shrink it to a point continuously like this, okay, let me show this in the same figure so that we can save some time. If you can shrink this loop continuously to a point, then it's called this topological space is a simply connected space, or simply connected. If you're dealing with regions, you call it a region, but we are dealing with topological spaces, so we call them simply connected. And if it has holes inside, for example, let's take this space and let's make a hole like this. So this is your hole. And if you consider a loop like this, you have to stop your shrinking at this boundary, the boundary of the hole, right? You cannot shrink it even anymore, because at that point you would be outside this space if you try to do that. So this is not a simply connected, not simply connected space. And we'll define this more, in a more precise manner when we study some homotopy. And these are all just preludes to that. So I think we are well past our due time. So should I stop here or should I continue? I have like 2 more topics left. One is the topological invariant, and another one is the homeomorphism. So do you want me to continue or do you want me to stop?
For me, it would be good if we stop today.
Okay. What about the rest of you? Everyone wants me to stop?
By 2 topics, how long does that mean? Like 2 more definitions, or?
One more definition, and yeah, I have to talk about the Euler characteristic a little bit. So should I continue or should I stop?
I guess not. Like, we've covered a lot of stuff that is very like math heavy.
I doubt adding 5 more pages would be a good idea here. 5
Okay,
pages.
so I think we should stop, right?
Yeah.
Yeah.
Okay. So let's stop.